You are given a non-negative integer written as a digit string, and an integer k. Remove exactly k digits so the remaining digits form the smallest possible number. The answer must not have leading zeros. If every digit is removed, return 0 as the string 0. In the example, number is 1432219 and k is 3. Removing the digits 4, 3, and one of the 2's leaves 1219, the smallest number you can make. Example 2, number is 10200 with k equal to 1. Remove the leading 1 to get 0200, which becomes 200 once leading zeros are stripped. Example 3, number is 10 with k equal to 2. Both digits are removed, so the result is the string 0. To build the smallest possible number, our highest priority must be the digits on the far left. As we scan from left to right, we look for relationships between neighboring digits. Here, the number increases from 1 to 4, but then immediately drops to 3. That 4 represents a localized peak. Because it sits in a higher value position than the 3 following it, keeping it makes our overall number inherently larger. By greedy elimination, we drop that peak. The digit 4 pops out of our sequence, and our remaining removal allowance drops by 1. Instantly, all subsequent digits shift to the left, replacing a high leading digit with a smaller one, dropping our overall value significantly. This strategy creates a continuous cascade. We maintain a strictly increasing, or monotonic, sequence of digits. Every time an incoming digit is smaller than what we just collected, we ruthlessly discard the larger preceding digits until the trend is corrected or we run completely out of operations. We must also account for two crucial structural edge cases. First, if our number is already strictly increasing, like 1, 2, 3, 4, there are no peaks to drop. In that scenario, we simply slice our remaining removals off the very end of the number. Second, if our removals leave a 0 stranded at the absolute front, we sweep it away, ensuring our final result is a valid, cleanly formatted integer. One last edge case: if k removes every digit, nothing remains. Return 0 as the string 0, not an empty string. We translate our intuition into code by leveraging a deque, which will explicitly maintain our increasing order of digits. We initialize an empty deque to serve as our container, alongside our rolling removals counter, allowing us to build our optimized number from left to right. Next, we iterate through every digit of the input string. Before adding a digit to our deque, we run a lookback check. While we still have removals remaining, and our deque isn't empty, and the back element is strictly greater than our current digit, we have detected a localized peak. We ruthlessly pop that larger element off the deque and decrement our counter before finally appending our safe digit. Once the main loop concludes, we must clean up two vital edge cases. First, if our digit sequence was already strictly increasing, our loop won't have used all operations. We handle this by popping any remaining removals right off the back of our deque. Second, we join our characters into a single string and strip away any leading zeros to guarantee our output formatting is a valid integer representation. Finally, we evaluate our process string for our return statement. If our aggressive zero stripping or our deletion operations wiped out the entire sequence, leaving our string completely empty, we safely default and return a single character string of 0. Otherwise, we pass back our optimized minimum string value, completing our algorithm in a single linear pass. Let n be the length of number time is O of n. Each digit is pushed onto the deque once and popped at most once during the scan. Space is O of n for the deque, which can hold up to n digits when the input is strictly increasing. Function remove k digits takes the digit string number and removal count k. Create an empty deque to build the answer from left to right. Loop over each digit in number in order. Before pushing, while removals remain and the deque is not empty, and the back of the deque is strictly greater than the current digit, pop that back element off the deque and decrement k by 1. Push the current digit onto the back of the deque. After the scan, while k is still positive and the deque is not empty, pop from the back to drop trailing digits, decrementing k each time. Join the deque into one result string. Strip any leading zeros so the output is a valid integer. If nothing remains after stripping, return the single character string 0. Otherwise return the optimized result string.